He came back to Sweden and is at KTH and is professor since '88. It's difficult to list all his contributions and awards in polynomial time, but to name a few, he's a member of the Royal Swedish Academy of Sciences since 2001. He's a fellow of the American Mathematical Society since 2013. He gave the prestigious Erdos lecture in the Hebrew University in Jerusalem in '99. And remarkably, he's one of the two researchers who have won the Gödel Prize twice. So he won the prize in '94 and 2011. Each time, actually, with a single author paper. That's quite remarkable. In '94, the prize celebrated his work on lower bounds on the size of constant depth Boolean circuits. And in 2011, his work was related to optimal inapproximability and the PCP theorem. So it's a great honor and it's a great pleasure to have Johan here at Colt and to have him at KTH as well, actually. So welcome and welcome, Johan. Tack.
Thank you very much for this very nice introduction. And as things are, I'll be, I'll return to this. So first of all, I'm very happy to take questions during this presentation. There's many of you, but if you don't understand, probably many other people don't also. So please don't be shy. And apart from inviting me, the organizers said that I can speak about whatever I want. It doesn't have to be related to learning. So what I picked was my favorite results, which happened to be the just mentioned Gödel prizes. And on top of it, I can be completely biased. I won't survey things. I'll just mostly speak on my own results. So questions might keep me honest. So let's go to the first one. So this is, what I did my thesis on in the 80s, and it's small depth circuits. These are Boolean circuits. We have, zeros and ones. We have negations. We have AND gates. We have OR gates. So I'll use N to be the number of variables, D to be the depth, and the size will be capital S because that's the largest number. And here's depth 3, 6 variables, and so forth. So why study small depth circuits? Well, I think over the years I've sort of been more and more enthusiastic. They're actually interesting in their own right. We should know how well small depth circuits compute various functions. And back in the 80s, we felt differently. We felt, this is just the first step. We'll knock off small depth circuits, then we'll do NC1, then we'll do polynomial size circuits, and soon we'll know everything about everything, which did not completely materialize, but that's... And for those who care about, relativized complexity, oracle results, if you want to do something interesting about the polynomial time hierarchy, then in fact it's good to have these lower bounds. So what do we want to do? We want to prove lower bounds for explicit functions, and the favorite function is parity. And we also want to prove that depth k is more powerful than depth k minus 1. Just to get a sense of the audience, how many people know how large circuits you need of depth 2 to compute parity? Okay, not so many. And I was going to ask depth 3, but that's probably we still have one volunteer here. Great. So that's just to get a sense of where we're going. Okay. So depth 2, I claim, is easy to understand. Depth 2 circuits. What's a depth 2 circuit? Well, there are actually two types. Well, I forget to say something important on this slide. We have alternating layers of ORs, ANDs, and ORs. Because if an OR gate feeds into a new OR gate, then in fact it's easy to see that you can just feed the inputs of the first OR gate into the second one and nothing changes. So we have AND gates, either an AND gate up top or an OR gate up top, and these are CNFs and DNFs. If you negate one of these guys, you get one of those guys and the other way around, so it's sort of equally hard to produce, to study this. And let's see how this works. So if you have an OR gate of ANDs, and suppose you're trying to compute parity. Could this circuit, for instance, compute the parity of 4 variables? No, why not? Well, let's look even at this AND gate, you know. By fixing 2 variables, you can make that AND gate 1, which in fact makes the circuit 1. And you can't just fix 2 out of 4 inputs and determine the value of parity, right? Get some nods there? Okay. So in fact, you need, each gate at the bottom needs the full, you know, needs the full fan-in to able to compute parity. And in fact, this sort of means that for each input that makes the parity 1, or each input that makes parity 0, you need a gate at the bottom, and that means you need a fully exponential size to compute parity by a depth 2 circuit. So all who didn't know this, did you learn this now? So that's... So this is just, you know, once you sort of think about the depth 2, you know, how it works, the inputs and the outputs. So now let's try to at least be positive. Let's to make a small circuit of higher depth that computes parity. Okay. So let's see how to compute parity of depth 4 to start with. And I'm going to have this in picture soon. So let's think of computing parity as making things of groups of square root n, compute the parity of each group, and then take the parities of the groups. Okay. So that's sort of a depth 2 circuit of fan-out square root n that you can make compute parity. And once you, but we don't have parity gates, right? We have AND OR circuits, so we need to make these parity gates into something else. So but we already knew from the previous slide that if parity of a certain number of variables at an exponential cost, we can make it into an AND and an OR gate. So let's see this in pictures. N happens to be 9 here, so you make a parity tree of arity 3. And now you can take each of these gates, which has a small plus in, and you probably can't see it in the back, and make it into a depth 2 circuit of size 5 in this case. And each of the bottom ones also. Okay, and this computes parity, which I sort of cheated you by a factor of 2 because you need some internal negations here, which I don't love, but let's not worry about this point. So, but you can be smarter. Okay. And the question, how do you smarter? Well, before I said you can compute the parity either by a CNF or a DNF. And suppose you make this top circuit a CNF. So it's an CNF is an AND of ORs. And you make these guys in the bottom DNFs, which are ORs of ANDs. Then in fact, all these guys in the middle will be ORs. You'll have ORs feeding into ORs. You're happy with this? So this means you can actually get depth 3 here. So you can get depth 3. Okay. So how do you do this to depth k? And we have one person who cannot answer this question. Yes? It's not a problem. So internal ORs can always be gotten rid of at the price of 2. So the question is, does internal negations matter or not? So the point, if you make 2 copies of each gate, one computing the original function and one its complement, you can sort of use the one you need and then sort of double the size of the circuits without increasing its depth. So that's internal negations do not matter. Okay, so that's the factor of 2 blow up that I've sort of glossed over. Okay, you happy with this? Good. So how about depth k? I mean, now you want to compute parity in depth 4 instead. In depth 3, I could get 2 to the square root n. What would you get in depth 4? Yes? Yes. And the way you do it, of course, is that you start, if you have k, you take a k level depth k parity tree, and then you compute them by exponential blow up. You can replace each gate, and then you make sure that you have alternating ends and DNFs and CNFs, and then you get just depth k plus 1. Okay. So for the parity result, this was what I proved in 1980 and eventually got this first Girl Prize for, is that this is tight. This was, first done by first Zach Zipser. Yao had some intermediate result, but then I got actually a fairly tight result. Of course, you can only sell to mathematicians that this is a tight result because this omega has a 10 in it. So, I can't distinguish size S and S to the 10, which sort of matters a little bit in practice. But among mathematicians, who cares, okay? And we also had a similar result for hierarchy things, that if you want something that's even a read once formula in depth d, you'll get sort of this sub-exponential type blow up if you want to do it in depth d minus 1. Okay, so this was sort of great, we felt very happy about this, but then there's this question, about average case complexity. Computing something in the worst case is good, but suppose you can make something correct in 99%, then, you can almost compute it and it's not such a big difference in practice. So you really want, that for any circuit in the class, it computes your function essentially with probability half. Of course, you can always compute something with probability half, because you either output the constant 0 or the constant 1, and one of these will actually be, 50, will correlate at least a half. So but you want it to go to be essentially 1/2. And in fact, for parity, we were getting pretty good results already in the 80s. We were sort of getting an increase over a half that was sort of inverse to the size we were proving. So it's 2 to the... And this we could get for very large circuit. If you just took the square root of the size, you get something that couldn't at all compute parity. Or in this sense, not at all. But the funny thing, if you took a really, really small circuit, we didn't get really better bounds. You could change the d minus 1 to d minus 2, but it was sort of a little bit fishy. But on the other hand, for this hierarchy result, the functions we were using were very easy to predict on a random input, because they were almost always 0 or almost always 1. So the constant circuits would predict this incredibly well. And that sort of seemed very inherent in these methods. So as I said, something was a little bit fishy because ITI had proved stronger bounds. So if you had just polynomial size, then in fact ITI had proved something that was almost exponentially small. And something I can remember at the time of my thesis feeling, I don't know if did anybody of you try to read ITI's paper? Yishai? I tried. This is a very difficult paper. One of the main motivations is to avoid reading this paper, and it was so embarrassing that he could actually do things I couldn't do. And the hierarchy results, I don't remember what I thought. I posted as an open problem in my thesis. It was sort of had a nice application. It would namely say that the polynomial time hierarchy was, had an infinite number of levels relative to random oracles. I did care, but it seemed completely out of reach. And what happens now is that 30 years later, I return, and then I could suddenly get the correct, I'll tell you in the next slide, the correct bound. If the size is really small, you just have a log s to the d minus 1 in the exponent there. That sort of takes away the n. And the funny thing is that when I proved this, it was proved independently at the same time by Impiglazzo, Matthews, and Paturi, which is sort of not as curious as I thought, because there was an intermediate paper which got a horrible bound, but at least it sort of said that something was going on, so they had some of the ideas. And let's see if I can convince you how to compute parity with an advantage. So let's now you have very many variables. You have you want to create a very small circuit that actually have some correlation with parity. So what you do is you divide your inputs into groups that's just large enough so you can compute the parity on each of these groups. Okay. So as we remember, this is log s. So if we want size s, we want depth d, we can compute the parity of log s to the d minus 1 variables. And then we just take the OR of these results. And this is a circuit that almost always outputs 1, but on the rare occasions where it outputs 0, each of the parity groups has parity 0, so the overall parity is 0, so we're in fact correct. Okay. And this exactly gives this correlation without, of course, without the constant there. Okay. You're happy with this? I see some puzzled looks. Right? Because once you have depth t, taking the OR of as many things as we want, that doesn't increase the depth, doesn't really increase the size, and so, no? Anybody, you're not happy with this construction? Anybody's trying to understand it and not getting it? Did anybody get it? Right? So you're computing parity of groups, and you make the group as big as you can afford to actually compute it exactly, and you just take the OR of the results, and that's it. We get one nod here. That's an infinite improvement to just a minute ago. And in fact, this average case result, I was beaten by Rosman, Serveggio, and Tan. And in fact, you can get the average case result you want. You can get, a correlation which is not exponentially small. It's only polynomially small, but this turns out to be the best you can do because it's a read once formula, and you can always get the correlation by just removing the output gate. So I was beaten, and they could get it up to depth square root log n, and I managed to get it up to log n over log n, which is the tight result. So I tell you a little bit about the proofs, what goes into the proofs of these things, and try to understand why didn't we prove these things 30 years ago when we should have proved them, and why do we suddenly get smarter with age, which we don't, by the way. Okay. So in order to do this, I have to tell you a little bit how you prove lower bounds for small depth circuits. So there are two ways to prove lower bounds for small depth circuits. One is by restrictions. And the restriction is you fix the values on most variables in the circuit and see what happens. And the other one is by polynomials. And this is sort of saying that the output of a small depth circuit is in fact well approximated by a low degree polynomial. This first thing was done by Sipser. The second method was done by Razborov. And we won't discuss this because actually what we're going to do is we're going to do restrictions. So let me tell you a little bit about the restrictions. So as I said, what our restrictions is just fixing variables. It's extremely simple, but we need some notation. A typical restriction will be called ρ. And it will be a probabilistic restriction. We won't really know how to simplify the circuit always. So what we'll do is we'll keep a very small fraction of the variables. And these will be denoted as stars. And then the other ones we're going to get 50-50, and we're going to either fix them to 0 or to 1. And this is called RP because P is the parameter where we keep things. So what happens, why are restrictions good? So restrictions are good because they simplify circuits. They manage to prove something called a switching lemma. How many of you have seen a switching lemma? Not so many, good. So we'll do the switching lemma. And this technique will be useful for anything that remains non-trivial if you fix variables. So the reason parity is good is that if you fix some variables, whichever subset of the variables you fix, parity turns into the parity of the remaining variables or the negation of the remaining variables. So all the lower bounds I say, or the lower bounds I will say will remain true for this. As long as something is trivial when you fix the values of most variables, lower bounds will apply for this. So let me have the switching lemma. I'll need some water. Now you can look at the switching lemma in pictures. So what you have is that, of course, any function can be written in ands of or an or of ands. And it can be that functions have a nice representation in one, but not in the others. But what the switching lemma manages to do is to switch from one representation to another. So if you have an or of ands, and the key parameter here is that the ands are all small, which I'll use the parameter t, you can switch it into the other side as an and of ors, where all the ors are of size s. And the probability that you fail to do this is exponentially small in s, so provided that p is small enough. Are you happy? So if 5pt, let's think of p as 1 over 10t, then this is a half. So with very high probability, you'll get something that has a small bottom fanning. It's exponentially vanishing in the fanning of the bottom layer you allow. Okay? Yes? Yeah, so for any depth 2 formula, and the only restriction is bottom fan in t, you fix the values of most its variables, and to zeros and ones, and keep a p fraction. And if this fraction is small enough, you can convert it into the other type. So it's a sort of, yeah. Yeah, it's over a random restriction. So this choice, we're going to keep a fraction p, and for the others, we're going to randomly do zeros and ones. So we're those two choices. Well, so you have a function which you originally computed by this. And then you sort of, give zeros to most things here, or zeros and ones, and keep a very small thing. And then of course, it's still computed by a formula that looks like this. You just do the trivial local modifications. But it turns out that you can flip it into the other one with high probability. And this is sort of the magic. I don't know if I can say it better. Good. Thanks. So let's see how we can use this to prove lower bounds for circuits, okay? Oops. So you should think of this, that S will be equal to T, let's do it in pictures instead. So let's try to prove a lower bound. So let's now try to a depth 3 circuit that's not supposed to compute parity, okay? That we want to prove doesn't compute parity. So what we do is that, but it has small bottom fanning, okay? This is not very significant. You can get rid of this, but let's ignore this point. So you hit it with a random restriction for RP for a good parameter P. And then you can look at any depth 2 subformula here. Okay? So we can switch it. Okay? Except with exponentially small probability. And the same goes for the second one. You can switch it. Oops, should never do this. This one happens to switch to just a constant 1, which is actually will happen with 50% of the cases, you'll get a constant. And this guy switches to something which has bottom fan in 1, which will also happen a good fraction of the time. So now I just move, now it's exactly the same circuit as I had at the bottom of the previous ones. But now you see, we have two adjacent levels of ANDs. So we can just remove them and let all the ANDs feed into the top AND gate. And we suddenly have a depth 2 circuit. Okay. And on top of it, we have a depth 2 circuit with a small bottom fan-in. And this originally we know couldn't compute parity of the remaining variables if the bottom fan-in is smaller than the number of remaining variables. And that sort of is the proof for the depth 3 case. And then you do by induction. For those who didn't see this proof. Yeah. So let's see why this gives average case hardness. Yeah. So take any circuit of depth D. If you hit it with a random restriction with the right parameters, I won't bother you what the parameters really are, then in fact you're going to wipe out one level. You just do what I said on the two lowest levels, you switch there and then you collapse the adjacent levels and you get rid of one level. And this is going to happen with high probability that you're going to do this switching. And if you repeat this D minus 1 times, you're actually going to get down to a depth 2 circuit with a small bottom fan-in. So it has no correlation with parity. So with very high probability, after you sort of fixed almost all the variables, you have no correlation with parity. And that sort of means that the overall correlation with parity is controlled by these failure probabilities. So here you need the fact that if you sort of randomly set almost all the variables to 0, 1, and keep a few, and then repeat this process, eventually you're going to get a uniformly random input. Composing a restriction with sort of fixing the remaining variables randomly, that's sort of a random setting in the first place. So the crucial thing is here to really, we're very happy with this exponentially small failure probability, but this is sort of what controls what we get. And in fact, if you looked at the parameters, for something, you're going to do this D minus 1 times. So to have something remaining at the end, you need a P that sort of, you can do it D minus 1 times and still having a probability 1 over n for each variable to keep it. And you need this S, the S and T's are the same, so you need, S can't be bigger than 1 over this probability, and that's sort of the bottleneck, and that's how you got the result I described on the first page. And you can't really improve the switching lemma. It's easy to see that what I say up to this 5, this dependence on P and T and S are optimal. So then you're faced with that, and what I didn't do 30 years ago is that then you would need to read Daity's paper, which I did not do. So you need something more. And now I'm going to summarize what I did 30 years later in a slide. If you look at the proof of the switching lemma, the fact that it fails is a stupid local property. Okay? And what you do is you just go over these depth 2 circuits, and every now and then you'll have a failure. And it turns out that you can fix this by just fixing a few variables that's involved in this very subformula. So what you can do is that if you have lots of depth 2 circuits, and these will be all the depth 2 sub-circuits of your formula, and you hit it with a random restriction, and you want them all to switch, you can sort of deterministically make sure that they all switch by just fixing the values of some more variables, which I call a set U. And the only thing that remains that's probabilistic is how big the set U will be. How many do you need to fix and how big will it be? And it turns out that you can now just prove a similar probability to what we had before for the probability not switching by the number of things you have to sort of extra you have to add, and then you'll be fine. And once you've done this, you're sort of home free, you know. This lemma, once you sort of formulate it, I'm sure I could have proved it 30 years ago, but I didn't think about it. You have some rather delicate conditional probabilities that you don't want to do, but you do, but once you've done it, the correlation sort of just follows and you get the optimal result. So what do we learn from this, you know? First of all, we should never give up. You know, if something is fishy, you shouldn't put it under the carpet and just forget it. You should continue thinking. And if you ever need a switching lemma, if you happen to be interested in small depth circuits, if the probabilities aren't good enough, think about adding some, you know, fixing some extra variables, and you can do even more things. How am I doing? Yes. No, so you're thinking you have a fixed formula, and then you're thinking of a random input.
What if I care that some of the inputs are in a different probability that not uniformly at random? Because maybe I care that some part of sound doesn't respect this kind of non-uniform inputs. Maybe I'm not calculating her response a huge part of my space.
Yeah, but you have to, I'm sure you could prove something. The question is if you have a different probability distribution. Of course, there are some probability distribution where parity is easy.
My questions are like, are there some kind of distribution where it's more relevant practically than uniform?
Well, you know, now we're getting into practice here. Yeah, I don't know. That's always the problem, you know, which probability distribution do you want to calculate it over? But I'm sure you could prove something. Yeah. Yes.
So, can you somehow relate these constructions to boosting? A little bit better than 50%, and then if you combine a bunch of those to build a better Approximation period.
Okay. Yeah. No. So the question, if this is related to boosting, well, boosting is really sort of taking a threshold, right? Taking a majority vote. So now you get into the question, well, majority is harder to compute than parity. Okay? And you can prove it by this. And the question is, suppose I give you majority gates. Now you get into this. Suppose I give you, you know, how hard is majority? It's at least as hard as parity. Suppose I give you parity gates. Can you compute majority then? And the answer to this is no. This is what Rasborov proved by this approximation by the low degree polynomials. But the converse, if I give you threshold gates, then we can't really prove any lower bounds. That was sort of the next logical step. After we could do the AND gates and the OR gates and the parity gates, we wanted to have unbounded majority gates. And this, if you go beyond depth, depending if you have small weights or large weights, if you go beyond depth 2 or depth 3, we can't prove lower bounds. So this was the next thing. I had a bet with Andy Yao that we would sort of prove that something was not computable by constant depth circuits with majority gates in the 80s, and he gave me dinner at a very nice restaurant 2 years later, and it still hasn't been done.
Another 30 years.
Yeah, another 30 years. So no. I couldn't parse that online when I'm speaking, but I'm sure you're right. Okay. Okay, maybe I took it the wrong way, but thanks. Okay. So let's skip parity now. So let's say something about the average case hierarchy theorems. So this gets harder, or more subtle in the sense that now we have two circuits. Parity, you know, the function we were computing played really no role. The only thing we wanted from parity is that if you fix most inputs, parity remains parity. But in the average case, you know, the hierarchy results, the function we want to compute is by definition computable by small depth circuits, something of depth D, which is probably quite small. While the thing that we're sort of competing with is something of depth d minus 1, which is incredibly much larger. And the only thing we can sort of hope, sort of having seen, is that it will have small bottom fan-in, and maybe this could be useful for us. And now we sort of have to make sure that we keep the defining circuit nice, and we while destroying the competing circuit. On top of this, if you sort of want to fix some of the inputs, you know, we want to make a restriction, and in the end we want a uniformly random input, there's almost no way instead of fixing the inputs randomly in the first place, right? We want to use an RP restriction. There are really no other options there. Because if after making a few restrictions, we still want to be looking at a random input. I'm not sure I'm making this right. We want to have a uniformly random input after, you know, doing our restrictions and so forth. And it seems like these restrictions have to be uniform. But this won't work because that would really trash the defining circuit, just immediately kill it. So let's see how to even to restrict the inputs to a single gate in an interesting way. So I have a single AND gate here. And the way I'm going to pick inputs to is I'll first pick a non-empty subset of the inputs. I'll call this set S. And then I'll say that for all variables in this subset S, I'll identify them with a single new variable Y. And the other ones I'll set to 1. Okay, so what will this do? Well, for sure, this little gate will now take the value of Y. Okay, because almost all the inputs are 1s, but the ones that are not 1s are all the same value. And on top of it, if we later set Y with the correct probability, which is actually 2 to the minus m, if we set it to 1 with this probability and 0 otherwise, almost surely, we're going to get a uniformly random input. Okay. So this is a very funny two-stage process of picking a random input. First, we'll put a set of variables that we said, these are all going to be equal. I'm not going to tell you what they are right now. All the others will be 1. And then I sort of flip a very biased coins where I'm going to make all these 1s or all these 0s. Okay. And this turns out to be the thing to use. So this was what Rossmann, Serveggio, and Tan did. They called it projections. So we'll set most of the variables to constants. We'll just have a gigantic identification of variables either, you know, have the same variable in many places. And then we can actually use the restrictions that were sort of done in the worst case. And then it turns out that, well, this is sort of a technical comment. It's not so easy to work with 0-1 inputs. You'll have very biased inputs. But you can simulate biased inputs by, you know, 0-1 inputs by just taking the AND of the suitable number of guys. So now you can actually see what now you want to prove a hierarchy result, you just take the natural function, you take an AND OR tree of the right fan-ins, and it's, you know, just a read once formula, and this is the thing we're going to work with. Yeah, let's ignore this. So you'll just have to, let me skip also this. So something, why did I do this in the first place? Well, RST, you know, proved this theorem, and I wanted to figure out what it was doing. And even if their paper wasn't as hard to read as ITI's, reading is getting even more boring as life goes on. So you try to distill the main ideas. And that's how I sort of redid everything in my own terminology, and I sort of managed to get another square root log n factor out of it. So I think it's much more fun to prove your own theorems than reading other people's papers. And on top of it, I think, you know, if you're ever into small depth circuits, switching lemmas are very versatile, you know. You can always prove a switching lemma. And what did we learn from this? Well, we learned that, you know, we learned the theorem, But I also learned that, even if you want the output to be uniformly random, you can do it in very tricky ways. And the tricky way that you in particular did was to pick, identify some of the inputs, and then you get very, skewed probability distributions. And I wanted to say something about the approximation also, so let's just pose one open problem for circuits that I thought would have been done, that was open 30 years ago, is equally open today. Suppose I just do depth 3. This actually gives you lower bounds 2 to the square root n for parity. Suppose you want to do something that's significantly better, 2 to the n to a constant that's greater than 1/2. This is still unknown after 30 years. And it might be easy, who knows? Yes? So you want to prove a lower bound that's better than what you get for parity. So 2 to the square root n in depth 3, 2 to the, cube root in depth 4, and so forth. Yes, because we know the results are tight for parity, right? So, well, you're such a materialistic community, you'll get infinite, your name will live forever, or at least, a decade. But it seems like you need a new technique, and I think this, would actually be useful. If you could actually do this, yes. Yeah, well, so there are lots of, so a random function will do, of course, by counting argument, but we want an explicit function inside P. So, but take there are functions that we think requires exponential time for, just real computation, right? Of course, they won't be able to do them in depth 3. So, but of course, now we're in a very low-level model with bits and so forth. So I don't know what the best function to use would be, but take any, take an encoding of, clique or some. Well, the clique you have to be a little careful because there's a square root there, but something that requires exponential time. So I'll speak a little bit about approximation. And so this is now, if you lost on the constant depth circuits, now we're doing some completely different. Okay, so I'll tell you just my favorite problems here, some of them. Yeah. So how many of you know the PCP theorem? Good. So this is a great theorem, right? So this says, if you have we all know how to check NP statements. And you have a normal, you can think about it as a verifier, verifying a proof. But now we want a probabilistic verifier that reads 3 bits. Okay, and this you can still make, a probabilistic verifier that always accepts a correct proof of a correct statement, but rejects any proof of an incorrect statement with a constant probability. And on top of it, you can make this constant probability. Oh, I got it wrong. Rejects, this is accepts. It should have been 3/8 rather than 5/8. It rejects with 3/8. Okay. So this is really an amazing theorem if you didn't. So I won't use this. This is just sort of the result that actually sort of started this amazing areas of inapproximability. So let's take our favorite constraint satisfaction problems rather than talking about constraint satisfaction. That is 3-sat. We all know 3-sat. It's NP hard, right? Suppose you want to approximate 3-sat. So I give you a formula, and I actually guarantee you that this is satisfiable. There's some assignment that satisfies all the clauses. And now your task is to efficiently satisfy as many clauses as possible. What would you do? And I want to guarantee. Pick at random, I love these algorithms. So we'll pick a random assignment. It doesn't use the promise. It doesn't even look at the formula. It just picks things randomly, and you'll satisfy each clause with 7/8. And this is the best you can do, right? So a theorem of mine is from which got the other Gödel prize is that if you want beat 7/8 by any small constant, then in fact this turns out to be NP hard. So this extremely stupid algorithm is the best you can do. But now you're probably not maybe so interested in 3-sat. You want sort of to use it for further reductions. And what's really good with 3-sat is that its clauses of size 3. You have 7/8 is sort of an okay constant, but not so great constant. So now let's look at other problems that we might use for starting points for reductions to prove that your favorite learning problem is hard. So one problem that I really like is linear equations. You know, we all know how to solve linear equations. So I'll give you a set of linear equations, and I'll have the mod 2. And on top of that, I'll have 3 variables in each equation. And the interesting result is that now it's hard, even if I guarantee you that 99% of these can be satisfied by some assignment, it's hard to find an assignment that satisfies 51%. Okay. So this is, you know, still sort of 3 bits involved. We don't have an OR, but we have an XOR of these 3 bits. And then we managed to push this constant 7/8 to essentially 1/2. But unfortunately, we have to sacrifice that, you know, some of the constraints will be violated also in the good case. Okay. And, you know, what's magical with 2 here, suppose I actually look at linear equations mod m instead, then you can get the result, but you can actually push this, what happens, the soundness case to 1/m. And of course, these results are tight because, again, you know, we're competing against the random algorithm. The random algorithm will do half in the mod 2 case and 1/m in the mod 1/m in the mod m case. Okay, so this is my favorite. This is sort of good starting points for further reductions. So now I'll actually take. Suppose bits are so much better than big numbers. So let's describe a constraint satisfaction problem that's not so commonly known, but I want to phrase it as sort of the Hadamard case. And this, one way to view it is that you take, you know, the recursive construction of Hadamard things. If you haven't seen this, well, this is the Hadamard matrix. You know, you look it up if you didn't see it. So let's have the predicate being, you know, being a row of this matrix. So this is a 2 to the k by 2 to the k matrix. So I'll have a constraint on 2 to the k bits, and in fact I'll disregard this first bit, which is not so interesting. And so you have constraints on 2 to the k minus 1 variables, and there's only 2 to the k of these that are actually accepted. So this is a predicate. And Siu On Chan had this very nice result saying that also here the algorithm of flipping just things randomly is the best thing you can do. It's provably the best thing you can do. So it's actually hard to distinguish if you can make satisfy all the constraints of this type, or just sort of the random fraction. This is sort of the random fraction because there are these many inputs out of 2 to the k bits. So if you're looking for something which has a very low, it's a constraint satisfaction problem with a very low soundness, this is one problem to use. Let's see how we do. Let's take this one. So now let's take 5 sats. Now you have to think a little bit. 3 sat is a little bit of, it's good, but let's take 5 sat, but I'll have you an unusual guarantee that I guarantee that there's an assignment that satisfies G literals in each clause. And I ask you to find a satisfying assignment. Okay? And the question, you know, for which values of G is this an easy and a hard problem? And if I only guarantee you normally that there's something that satisfies the clause in the normal sense, you know, This is 5 set, and this is a hard, problem, so this is of course hard. On the other hand, if I guarantee you that there's an assignment that satisfies all literals in all clauses, it's very easy to find this because you can satisfy everything. But how about these intermediate cases? Now you have to work a little bit. So if I guarantee, for instance, there's an assignment that satisfies 4 literals in each clause, can you find it? You should be able to figure out. There are many clever people out there. So I guarantee you, I have this, right? There's some, I don't know if this is actually true, put this one, but there's some assignment that satisfies 4 out of these 5, 4 out of these 5. Can you find some, and I ask you now to find something that satisfies only 1 literal in each clause, right? So there's something that satisfies 4, but I want you to satisfy 1. Can you do this? I'm not going to stop talking until you solve this one, Yes. How do you do it? You pick one. No. Well, I can actually, you can reduce it to 2 set. Because you take all pairs appearing in each clause, and since there's something that satisfies 4 literals in each 5 clauses, as long as you take 2, one of those will be satisfied. And that actually gives you a 2-set formula. And 2-set formulas you all know how to do. Right? Now I got so many nodes, I'll continue. But so how about the remaining ones? I mean, the more I promise you, the easier it's going to be, right? So it can't, the only incorrect answer is that 2 is easy and 3 is hard. This can't happen. Right? That's the impossible one here. So 2 is hard, 3 is easy. I'm running out of time, so let me tell you the algorithm for 3. So Christos Papadimitriou had a very nice algorithm for 2-set. And the algorithm for 2-set is sort of the stupid one. Start with any assignment, and as long as there's a falsified clause, take the 2 variables in that clause and flip one of them randomly. Randomly pick which one to flip and flip it. Okay. So in fact, since there's some assignment that satisfies everything, this particular assignment has to be different from your current assignment in one of the 2 things, or maybe 2 of them. Which sort of means that if you look at the distance from your assignment to this satisfying assignment, it's at most an unbiased walk. So if it's different in both, you're going to get closer for sure. And if it's different in one, it's sort of a 50-50 whether you're going to get closer or not. So if you apply this to my 3 satisfied things out of 5, in a 5-set formula, take a falsified clause. The extremely good assignment that we're looking for in a falsified clause is different in 3 of the 5 things. So if we pick something randomly, it would probably be 3/5 will get closer, and we probably 2/5 we're going to get further away. So we're actually going to have an attractive walk, and within, in fact, linear time, then we're going to end up in a satisfying assignment. This is a very nice algorithm. Okay. And if it's exactly a half, if you go to 6-set and we have 3, then it's unbiased and you need time n². And in fact, you can make this deterministic. But the nice thing is that I proved with Parastrin and Venkat Guruswamy is that this is tight. If your guarantee is less than half, then in fact it's NP hard to find the satisfying assignment. So in a 7-set formula, even if I guarantee you can satisfy 3 literals in each clause, you can't find this in polynomial time. It's NP hard. And I just feel the reason we proved this is that this was going to be a great starting point for reductions. It's better than 3-set. It has to be useful. We sort of managed to use it for some small applications, but there are many of you here. You should use it. Other variants of we'll skip this. I want to. Do you know the long code, by the way? One last piece of it. This is a great invention of theoreticians. Okay. It's coming out of context now, but I'll teach you at least what the long code is. So if you want to code a constant number of bits by a big binary code as you want, then in fact what you can do is for code x you index a function by f, and for each function f you give the value of f of x. Okay. So this is coding d bits by 2 to the 2 to the d bits. And this you can afford for a constant d. So for instance, for 3 bits, you can code this by this 256 bits, and this blue 0 tells you that for this thing the parity is 0. And then I was trying to make this thing for 4 bits. And this is of course not the long code, it's only 132 of the long code. And you didn't even have parity, so there's no blue bit. But this turns out to be extremely useful in practice. Theory. And then, if I'm going to say something last, if you didn't these nice MP hard theorems that I proved, if there's something that I think should be tempting to use in further reductions, it's sort of the colorability. So people have spent a lot of time on color. If I give you something that's 3 colorable, and you want to color this with as few colors as possible, Avi Vigdisson a long time ago did square root n, and now it's improved by a sequence of papers, but it's still, n to some constant, with this constant is around 0.2, but it's not known to be MP hard, and I think this is an excellent problem to start with for reductions, because people have spent a fair amount of time at this. So you didn't see all the things, I'll give the slides to the organizers. There are many good starting points that maybe you don't know all of them. There are some nice other assumptions that you could use, but of course we shouldn't start using too many assumptions. This coloring one, people have at least spent a decade thinking about, so it sort of could be cautious. And that's the end.
Thank you very much, Johan, for this nice journey into your results. We need questions now. Please.
Do you know of any easy problems?
Well, there are lots of easy problems, I don't know what to say. Linear, sum of squares is the new thing that solves problems that weren't solved before. So if you're into, theoretical algorithms that runs in polynomial times, you should look at sum of squares.
Going back to other distributions for parity.
Yes.
If the vectors are promised to be uniform on sparse vectors, very few ones,
So the question is parity if you have very few ones. But you can if your promise on the ones is like that there are most t ones. This of course won't be easier than parity on 2t variables, right? And I would so that you get immediately some hardness results. You can't do more than polylog in polynomial size, for instance, if you have depth d. And I would suspect that that's the answer. Yes? Yeah. No, so you start, I need the PCP theorem through this label cover problem which I had on my slide, which is the model. So I don't know how to prove this theorem without the PCP theorem. And there's not a simple gadget reduction from 3 sat to this problem with the 2 out of 5 sat. So it seems to be a different, but it would be nice to see a direct proof of this. But it could be useful. Yes?
In the first part of the lecture, you talked
Yes? So the question is, what's the importance of this that switches all with high probability? The application I gave you is the main application. Somebody told me of a different application, but I forgot it. So, but it gives more, you know, it sort of says that this switching, which looks extremely powerful, in fact, what you get is not only the different type, you get a small depth decision tree, and on top of it, this is a very, you know, how should we call it? The deep branches are not, it's not a very bushy tree, you know, it's very sparse. So they might have some long paths, and that's what I sort of use. So it just gives you a little bit more structure there. Yes? Well, the question is how does the switching lemma relate to uniform and non-uniformity? So my circuits are non-uniform, right? Which sort of means that, you know, but if the circuits were uniform, the switching lemma is still true. So I'm not sure how to interpret your question. I mean, it sort of says, I don't care how these circuits were produced, they still switch. And of course, if your circuit is uniform, they switch, but then the switched circuit might not be uniform. Yeah, so this I don't know how to answer, you know. I don't know how to get the uniform circuit there. Yeah, I never really... somehow this switching is a little bit Boolean. So I would suspect no, I didn't work too much on algebraic circuits. But the fact is that AND gate, I mean, the reason things switch so nicely, if you manage to make an AND gate 1, and it feeds into an OR gate and it kills the gate on top of it. And this is sort of what's going on in a very subtle way. And nothing like this happens when you're sort of working with arithmetic circuits over a big field. So I would suspect there's no switching there.
More questions? If not, let's thank Johan again. Thank you very much. Thanks, it was great.